Hello everyone, myself Prunal and my partners are Jay and Akshita. We are here to present a presentation on renewable energy for sustainable development in Germany. Start with agenda. First we will start with introduction, then literature survey, then there are number of topics and finally we will discuss about the comparison of all of these systems and the conclusion. Introduction. As we all know, Germany currently lacks the renewable energy resources necessary to produce all of its future demands. And we all know that there are many devastating effects currently are happening due to the war between Russia and Ukraine. We have also worked on demonstrating the hybrid power system for fulfilling the load demand of city of Osnabrück, Germany. We will demonstrate three hybrid systems in this presentation. One is solar, another one is biomass, and the third one is wind. And there is hydrogen is common in all of these three hybrid systems. We have used Homer Pro software in order to simulate all these three systems. Literature survey. Hydrogen is a clean fuel that when consumed in a fuel cell it produces only water. A fuel cell produces electricity in an efficient and clean manner by utilizing the chemical energy of the hydrogen. Electricity, water and heat are the only byproducts in case of hydrogen as a fuel. Hydrogen can be produced from a variety of domestic resources. The most common methods today are natural gas reforming, electrolysis, and there are a few other processes also. Hydrogen production processes we have researched on four processes, namely electrolytic processes, biological processes, thermochemical processes, direct solar water splitting. There are number of another processes also which are under the electrolytic processes, biological and thermochemical respectively. Let's talk about electrolytic process in detail.
Hello everyone, my name is Akshita. Let's start with the electrolytic process for hybrid system. The process of separating hydrogen and oxygen from the water is known as the electrolysis. This reaction occurs in the device which is known as the electrolyzer. Electrolyzers are made up of anode and cathode that are separated by the electrolyte material. Electrolyte could be a different kind of material and which has a different properties which act as similar to the fuel cell. So we are using electrolytic process in order to create a hybrid system in Homo Pro. Our main goal is to create a hybrid system that include hydrogen with a particular renewable resources. Our first case is the solar hydrogen hybrid system. Case 2 is the wind hydrogen hybrid system. And case 3 is the biogas hydrogen hybrid system. Case study. For case study, we choose Osnabrück city, which is located in the German state of Lower Saxony. The average load demand of the city is 329.69 kilowatt with the peak demand of 657.44 kilowatt per hour. The yearly demand of the city is 2910 gigawatt hour. To meet this supply, we are going to use three different systems: solar hydrogen, wind hydrogen, and biogas hydrogen. We are going to supply this load by the 3:2 or 60-40 ratio with the respective renewable sources and the hydrogen system. The below graph show the daily load profile through the hours, seasonal load profile by months, and yearly profile by hours. Next is Homer heavy system component. This table shows components and their capacity. For case 1, we are going to study solar hydrogen hybrid system. So we use PV panel which has a capacity of 1164 kilowatt. For second case, we are going to study wind hydrogen. We use wind turbine which has capacity of 100 kilowatt hour. And for third and last case, we use biogas as a main resource. So biogas generator has 500 kilowatt hour capacity. We are going to compare all three hybrid systems. So we use fuel cell, generic lithium ion battery, converter, generic electrolyzer, and hydrogen tank, which have a same capacity for all three systems. Case 1, solar hydrogen hybrid system. Using sunlight, PV panels generate electricity which is directly supplied to the community load to meet the load demand, and other electricity is converted to the DC and supplied to the electrolyzer to for electrolytic process to generate hydrogen. Then this produced hydrogen is stored in hydrogen tank. Here, reformer is also used to produce high quality of generator, and this reformer use same hydrogen tank to store that hydrogen. Now here fuel cell use fuel as hydrogen and generate electricity to again supply the community load. The figure 3 shows the schematic diagram of solar hydrogen hybrid system in Homer software. Now Homer simulation result. After performing multiple simulations in Homer's software, we got most feasible and economical solar hydrogen hybrid system. For this solar hydrogen hybrid system, total NPC, total net present cost is 33.3 million with operating cost of 1.15 million per year. The levelized cost of this solar hydrogen system is 0.88 USD. Electrical outcome. For Asamberg city, average global solar radiation is 2.67 kilowatt hour per meter square per day, as per Homer NASA resources. By using this solar radiation, PV generates 58% of the total load, and other fuel demand is supplied by the fuel cell using the hydrogen. The excess electricity for this system is 9.24, which is quite high. But we can store this excess electricity, and we can use this electricity whenever there is no sunlight. The unmet electric load is 2037 kilowatt per year, and sorted capacity is 2806 kilowatt per year. Hydrogen production and consumption. With the help of electrolyzer and reformer, this system generates 3,55,577 kilograms of hydrogen per year. Among these, generic fuel cell use 3,33,931 kilogram of hydrogen per year. The remaining hydrogen is stored in the hydrogen tank. Nearly 6% of hydrogen is stored in hydrogen tank. The levelized cost of hydrogen production is 7.25 USD. Here, this graph shows the hydrogen production by the reformer and electrolyzer.
Wind and hydrogen system. In this part, we will try to make a hybrid system from these two energy, wind as well as hydrogen. We all know that wind power in Germany is a growing industry. So here in figure number 7, we can see that monthly average wind speed data of the Osnabrück city. So annual average is around 7 meter per second. So it is totally feasible to install a wind turbine at Osnabrück city. Beside that, there is a figure number 8 in which we can see that wind hydrogen hybrid system in Homer Pro, which consists of various parameters like wind turbine, battery, load, electrolyzer, hydrogen tank, reformer, and all. Homer Pro simulation result. The system architecture components and cost overview are shown in the above figure, figure number 9. In the cost section, top right corner, we can observe that the levelized cost is only 0.7855 US dollar per kilowatt hour, and the overall NPC means net present cost is around 29.5 million US dollar. We can see from the system architecture that there are total 13 wind turbines, each with a capacity of 100 kilowatt, have been used. Additionally, it is good that the base system and the proposed system are identical. Electrical output. In figure number 10, we can see the electrical output of wind and hydrogen hybrid system. We can notice that in the production side, hydrogen fuel cell consists, uh, uh, has a production of 47.2% and selected wind turbine produced 52.8%. Both have almost equal share of total production. Further, this system is also capable of fulfilling the consumption requirement fully, it means 100%, which we can also see in the table. We do have some excess electricity after fulfilling the load requirement. To be precise, it's 4.59%, which we can see in the table also. This is a normal thing, keeping integrity of renewable energy in mind. And it is always better to produce a little bit of excess energy, which we can use locally as well as some other application, or we can also store in the battery. Further, in the graph, we can also notice the production details of the wind as well as hydrogen production and consumption. We can see that the total amount of hydrogen produced by the reformer is almost all consumed by the fuel cell, and we do have some excess hydrogen remaining, but it's just 2.25% of the total production. And this excess hydrogen we can put back into the hydrogen tank. And from the graph we can notice one thing: the use of reformer throughout the year means each month is quite uniform.
Case 2. Biogas and hydrogen hybrid system. I have performed the simulation for this hybrid system in Homer Pro software, in which biogas generator is connected to the AC bus while fuel cell is connected to the DC bus. The load which we have to supply is connected to the AC bus. In this slide, I have also mentioned some properties for the biogas generator. The capacity of biogas generator which I have taken is 500 kW, while the fuel price for the biogas is 0.85 and the efficiency of the generator is 70%. After performing the simulation, I got some results which I will discuss here. First, cost summary. The NPC, net present cost for the system, is $7.35 million, while the initial capital for the system is $3.72 million. The least cost of energy (LCOE) is around $0.195 per kilowatt hour. After that, if I look through economic metrics for the system, the return on investment for the system is 33%, which is very high, and that means I can cover all my expenses for the system in only 2.4 years. Second, electrical output. This software takes into account the energy production from both the energy sources and energy demand in context of electrical output. The biogas genset produced 58% of the total power required, while the stored hydrogen produced 41.3% of total electricity required. When compared to the load demand, which was only 29 lakh 10,085 kilowatt hour per year, they produced 30 lakh 38,914 kilowatt hour per year. That means 100 kilowatt of lithium ion energy storage are used to store the remaining supply. Therefore, the annual amount of excess electricity is 0 kilowatt hour. As in the simulation, there is not enough excess electricity to produce hydrogen by using electrolyzer and reformer. So hydrogen tank is needed to supply fuel cell. It is presumed that hydrogen tank initially contains 50% of its rated capacity. So this storage tank has 130 ton of maximum storage capacity. In order to produce energy, the fuel cell uses this hydrogen from the hydrogen tank. As a result, the storage fell to 14 tons from 75 tons at the end of the year. Now I will compare three different systems on the basis of results which we got. From the table, we can say that the net present cost and the cost of energy for the biogas hydrogen hybrid system is very low compared to solar hydrogen system and wind hydrogen system. Along with that, excess electricity in biogas hydrogen system is only 86.3 kilowatt hour per year, which is comparatively very low from the other two systems. If I add to the comparison between three different hybrid systems, the mean electrical efficiency of fuel cell in biogas hydrogen system is very high, which is 83.6%, while the other two systems has only 14.3%. But the only drawback for the biogas hydrogen system is that the system is not able to produce hydrogen just because the system has the very less amount of excess electricity. In conclusion, from this simulation study in Homer Pro, we found that the best renewable method to fulfill Osnabrück city's load requirement is biogas hydrogen hybrid system. This is due to certain reasons like total net present cost, payback period, and the excess electricity. The solar hydrogen system and wind hydrogen system need more capital investment and operating and maintenance cost per year. That's why this system is not economically viable for Osnabrück city. In future, to get more better and reliable power system, we can also combine solar, wind, biogas and hydrogen all in one system.
Thank you for giving your valuable time to listening us.